I don't know if that's more efficient or low. The point is that when it gets into your stomach, the absorption in your stomach is very low. Because your stomach is not actually an absorptive organ, it's a digestive organ. And so it is lined with mucus to prevent absorption of most things. So most of the alcohol absorption actually occurs either in your mouth or in your small intestine afterwards. Small intestine water. If you really want to get drunk really fast, and this is actually from the movie, yeah, the large intestine is there for liquid absorption. That's its job.
Oh, right.
I've seen a lot of people come into the hospital drunk that way.
Yes,
Oh, yeah.
you can
That's
get alcohol poisoning really easily that way.
Like you, wait.
Rectally.
Yep. Yep. What's they get?
It's called a butt
It's like,
chug.
yep.
Yeah.
It's like
Yeah.
bone.
As has been immortalized by John Cena in the recent movie of cock blockers, or yeah, I think is what it is. John Cena, to prove his love of his daughter, to keep her from losing her virginity on prom night, butt chugs a beer. Because that's how you show your acting chops, is by taking a part in a really bad comedy movie.
So there was a kid in the fraternity that died from it because they were bonging beers in their butts.
Yeah. See, what? Okay, an idiot who wants to get drunk really fast.
Eating Tide Pods.
Yeah, like, one never has gone wrong by underestimating the intelligence of the average person. Like, a person can be very smart. Most people, in normal situations, not terribly smart, right? It's easy to make really dumb
Yeah,
decisions.
you get a group of people together and like, oh, hold my beer, watch this.
Yeah, exactly. The most dangerous, three most dangerous words. Hold my beer.
I got in
Something
serious
dumb's about to
trouble
happen.
with my friend, because my little nephew was right there, and I said, dude, hold my, and for the next half hour, little Ian, dude, hold my.
Yeah. Careful what you do around little mimic machines, because that's all children are, is mimic machines. All right, let's get back into chemistry, shall we?
It's applied chemistry.
It's sort of the border between chemistry and biology. Yeah.
I think most of us are nursing students or something, you know, we'll see all of this in the hospital.
Yeah, exactly. There will be a whole lot of like, really?
Yeah.
Shit.
Just,
How did you get that up there?
why would you do that?
Yeah.
The hamster, what?
Yeah.
All right, so molar volume. That 22.4 liters equals a mole of gas can be used as a conversion factor. So what this means is, I could ask you questions like, what's the volume of this many moles of hydrogen at STP? I could then ask a follow-up of, and now change the temperature of that, and what's the new volume? Oh, yeah. Why would I want to do that? Why would I want to take two concepts and string them together in the same question? This is just another way of writing what I tried to impart upon you earlier, which is the molar volume of a gas. It does not matter what type of gas it is. It does not matter if it's helium, oxygen, nitrogen. It will occupy 22.4 liters at 273 Kelvin in 1 atmosphere. Now the weight of that gas, that will obviously be dependent upon the weight of the molecule that makes it up. But a mole of that gas will have 22.4 liters of volume at STP, regardless of which gas it is. Hydrogen, carbon dioxide, butane, benzene. A mole of it will have a volume of 22.4 liters at STP as a gas. It has a vapor pressure, yeah. Volatile chemicals, they become gases. Calculating molar volume. So, what's the volume occupied by 2.75 moles of? Would it matter? Nope. What's the volume occupied by 2.75 moles of doesn't matter at STP, right? Of X gas at STP. Well, we have our moles. So how do we get that? Well, we need the molar relationship between moles and volume. What was that again? Well, we just had it. 1 mole is 22.4 liters, or 22.4 liters is 1 mole, right? Whichever one's more useful.
Use 3 basketballs.
Approximately the size of 3 basketballs, yes. Although answers in basketballs will never be correct on a test. 16.4 basketballs. No. Creative, but no. So, we take our 2 conversions. We have 2.75 moles, so we're going to use the liters over moles so that our moles cancel, and that gives us 61.6 liters of nitrogen. Here's the thing. Most gases that you guys are going to actually interact with are not pure gases. Most of them are mixed gases. The atmosphere itself is a mixed gas of all the things in it. So, let's talk about Dalton's law for partial pressures. It's a very simple application. For mixed gases, the partial pressures will always add up to the total pressure. It is arithmetic. So if we were to combine helium and argon together into one tank, if the volume stays the same, then the new pressure of that tank would be just simply the addition of the pressure of helium and the pressure of argon. This should make sense to you. Because what is pressure? It's simply the amount of times those atoms are hitting, coming into contact with the boundaries of that container, right? And so if we add enough things to create 2 atmospheres of pressure, with enough things to create 4 atmospheres of pressure, doesn't it make sense that you would just have 6 atmospheres of pressure? I mean, why would it be multiplicative? Why would it be less than that? It's like if I put a 5-pound weight on your chest and then put another 5-pound weight on your chest, you would not go, wow, that's 15 pounds. It would be 5 plus 5, right? Partial pressure for gases is exactly the same. What that means is the total pressure is equal to all of the partial pressures summed up. So, guess what this means? If I give you a total pressure, I could ask you for a partial pressure of a certain thing, as long as you know everything else, right? Like P1 plus P2 plus P3 plus whatever, how many more there are. If you know all but one, can you solve for that one? Yes. As long as you know all but one. 1 mole of nitrogen is 1 atmosphere. If we mix in 0.4 moles and 0.6 moles together, we get one atmosphere for that same volume. If we have 1 mole of gas in total at STP, the volume will be 22.4. It does not matter what gases are there. If there is a total of 1 mole of particles at STP, that is the volume. Knowing that, it means that if I was going to be very mean, you could take that understanding and do all sorts of hokey things with it. The air we breathe is a mixed gas. Nitrogen, oxygen, carbon dioxide, argon, water vapor, and any number of other things that might happen to be there. Ozone, carbon monoxide, a little bit of radon, if you're talking about your basement maybe. Fun stuff. It's a mixed gas. What we call the atmosphere is actually the sum of all of the partial pressures of all of those gases. pushing down and colliding with us, with our skin. So, if we have a scuba tank that has oxygen and helium in it, oxygen's at 0.45 atmosphere, helium's at 855 millimeters of mercury, what's the total pressure of that tank? What do you got to do? We want the total pressure, P sub T, in millimeters of mercury. So what do you got to do? Got to convert the pressure of oxygen from 0.45 atmospheres to millimeters of mercury, right? And then once you've done that, what would you do? You would quite simply just add them up. So, 0.45 atmospheres at 760 millimeters of mercury per atmosphere is 342. So 342 plus 855, and our total pressure is 1.2 times 20 times 10 to the third, or 1,200. No. Yeah, 1,200. They're rounding for significant figures here. Millimeters of mercury. That's chapter 8. We've got an hour and a half left.
Yeah.
So, because this was the hard part from chapter 7, right? This is the one that like, what, wait, what, huh, So let's do it. I find it's usually easiest to start with the first thing and keep going till you get to the end. So what do I mean by that? Let's balance number 1. What's the first thing you run into when you're looking at this equation? Sodium, right? Sodium nitrate. So, how many sodiums do we have on the left? 1. How many do we have on the right?
2.
2. So at a very minimum, to begin with, the first thing we have to do is this. Everybody see that? That does not mean that that is correct. But in order to make the sodiums balance, we need to put a 2 there. Right? So, if we do that, remember, nitrate is a polyatomic ion. So, we have now created 2 nitrate ions on the left side of the equation, on the reactants. How many nitrate ions do we have on the right side of the equation?
6. Or 2. Sorry.
Currently 2, because we don't have a number there, right? So, are we balanced for nitrate ions so far?
Yes.
Yes. So let's go ahead and put a 1 there, just so that we know that we've already checked that one, right? So, if that is correct, then that means we have how many atoms of lead? 1. How many atoms of lead do we have on the reactant side?
1.
1 currently. So we're good there. So that means we have how many atoms of oxygen on the left?
1.
1. How many atoms of oxygen do we have on the right?
1.
1. So, if we put that 1 there that we didn't fill in earlier because it's just there. So now, are we balanced?
Yes.
Yes. Doesn't that seem easy? Still getting a few like, maybe. Alright, let's try the second. Silver iodide. How many silver do we have on the left? Well, we have 2 on the right, right? So let's assume that we're going to put a 1 here for now, right? We have 2 silver. Yeah. We have 2 silvers on the right, so that means we're going to have 2 silvers on the left. So how many iodines does that mean we're going to have? 2. How many iodines do we have on the right? 3. Crap. All right, so what do we have to do to make the iodines and the silvers work? So we have 2 iodines on the left right now, but we have 3 iodines on the right. So we're going to need to go up to 6. Right? So in that case, how many of these guys over here on the right do we need to get 6 iodines? 2 of them, because there's 3 iodines right there, right? So if we put a 2 here, that gives us 6 iodines, right? But that means we need to come back here and change this. So now how many silver iodine do we need? 6. Whoops. 6. So that means we got to go back over here. 3. How many of these do we need? 3 to get 6 silver, right? Now remember, CO3 is a polyatomic ion. So, how many CO3s do we need over here on the left?
3.
We have 3 here. We have 3 here, right?
Yeah.
So that means we only need 1 of these. How many iron does that give us?
2.
2. How many iron do we have here?
2.
2. Are we done?
Yep.
So there's a good example of how you start at the beginning and then there's a, oops, wait, no. That just becomes your new beginning and then you work forward from there. Now I do have a question for you. What if I change this, that 6, to a 12, and this to a 2, and this to a 4, what needs to go here?
6.
Would that still be balanced? The ratio of all of those things would still be the same, right? The ratio of 6 to 2 is the same as the ratio of 6 to 1 is the same as the ratio of 12 to 2, right? The ratio that we're looking for, the correct balanced equation, is always going to be the one with the lowest whole number total. So if you have a test question or a homework question, it's going to be looking for the 6, 1, 2, 3 answer, not the 12, 2, 4, 6. Everybody follow? As long as you're looking for correct. If it was an aspect of which of the following equations is balanced, the 12, 2, 4, 6 would still be balanced, right? Versus a 12, 2, 4, 3, that would not be balanced, right? All right. What about number 3? The first thing we're running into is carbon. So how many carbons do we have on the left?
2.
2 of them. So if we put a 1 right here, because that means how many of these guys do we need over here? 2 of them to get 2 carbons, right? Now, this is going to get a little hokey because what can we're going to have, well, we can still do it this way. What's 2 times 2? 4. So far we have not just 4, but we've also got 5, right?
Oxygen.
So how do we do this? Because we've got 2 there, but also 2 there. All right. Well, before we worry about the oxygen, let's worry about the hydrogen. How many hydrogens do we have here? 4. So how many waters? Is there any hydrogen in here? No. Hydrogen's in the water, right? So how many of these water molecules do we need to make 4?
2.
2 of them. Bloop. Now, how many oxygens do we have? 2 times 2 is 4 plus 2 times 1 is
6.
2, so that makes 6 total, right? 4 here, 2 here makes 6. How many do you have right here?
2.
2 of them, so how many needs to go here?
4.
We need 4 more, and four atoms of oxygen in an O2 would be a 2. Everybody follow? So, if we'd have done that exactly the way that I suggested you do it, just start with the first thing and move on, you run into that problem. Holy crap, there's oxygen in both. Don't freak out about that. Just set the oxygen aside and keep going. What's the next thing on the left? Balance it on the right, and that might be all you need to know. In this case, it did, right? Because we figured out that with this much water, it gives us 6 oxygens. 2 of them are accounted for here, which means the other 4 has to come right here. And now we're balanced. Question?
So in solving these, you should always kind of go from like left to right as far as like looking at which.
Theoretically, you could
balance
start
first.
anywhere you want, but like I said, it's usually easy to start at the beginning and keep going till you get to the end. So I always start with just the first thing you run into. Whatever that first element is, just grab it and go. Start from there.
But that's, I don't know by saying it that way that you made it clear, start with the element, not with the polyatomic ion.
That's true. I mean, start with the first unit of something you can compare, right? In this case, carbon. And the reason why it's meaningful is because, yes, we weren't trying to balance the number of nitrogens separate from the number of oxygens. Whenever possible, identify your polyatomic ions, your sulfates, your phosphates, your carbonates, because those are probably not going to change, which means you can balance them as a unit instead of having to balance the P's and the O's separately. Now, you could get something that's complex enough where it does change. Something can convert sulfate to sulfite. Pull a couple of oxygens out of it. It is possible. But chances are, especially at this level of technical difficulty, we're not going to be dealing with that type of equation. And even if we were, it'd be really obvious because there wouldn't be an SO4 on the right. You'd have an SO4 on the left. So for example, here's a polyatomic ion right there. Sulfate. And is it still sulfate on the right? SO4. Right? Now we know right off the bat if we had a problem, because if that was SO3, well, crap. They just got a little bit more complex, right? But it's not. It's still SO4. So we don't have to worry about sulfurs separate from our oxygens, because that's a polyatomic ion. It's going to move as a unit. So let's try this one. Start with the first thing and move on. We have how many zincs on the left? 1. How many on the right? 1. Okay, well let's go ahead and put a 1 and a 1 here then. Just for a placeholder, right? So that leaves us with 1 carbonate on the right. How many carbonates do we have on the left?
1.
Also 1. Which leaves us how many lithiums on the left? 1 times 2, right? Because there's a 2 right here that I'm sort of covering up. So that gives us a total of 2. How many lithiums do we have over here? 2. So we can put a 1 right there. Are we done? Well, all the spaces are filled up, but are we done? We haven't checked everything yet, have we? 1 sulfate. 1 sulfate. Now we're done. Because if it wasn't 1-to-1 for the sulfates, we would not be done. We would have a problem, right? And we'd have to go back, change all the numbers again, account for the sulfates first, and then work backwards. Probably would be the way that I would do it. Find the problem child, fix it first. Vanadium oxide plus calcium sulfate to calcium oxide and vanadium sulfate. How many vanadium do you have on the left? How many on the right?
2.
All right, well then let's put a 1-to-1 there for now, right? So that leaves us with 5 sulfates How many sulfates do we have on the left? Or sulfides, excuse me, not sulfates, sulfides. 1. So how many of these do we need?
5.
That leaves us with 5 calciums. So what do we have to put here? 5. Which gives us how many oxygens? 5. How many do you have on the left? 5. So are we good? Yes. See how easy this is? Let's do number 6. Manganese nitrate and beryllium chloride to beryllium nitrate and manganese chloride. So how many manganese do we have on the left and the right? 1 of each, right? So let's put a 1 and a 1. So 2 chlorides here. How many chlorides do we have over here? 2. So we can put another 1 right there. That gives us our 1 beryllium here. How many berylliums here? 1. So we can just keep putting a 1 there, right? That gives us how many nitrates? 2 nitrates. And how many nitrates over here? 2. So are we good? Done. All right. For the first 6 things, tell me what type of reaction that is.
Double replacement.
For number 1, is it a double replacement? We have 2 dance partners, sodium nitrate and lead oxide. Who's lead dancing with on the right side? The nitrate. Who's sodium dancing with on the right side? Oxygen. So we have swapped. Sodium and nitrate are no longer dancing together. They are now dancing with the other partner. So it is a double replacement, right? How about, so for iodide and iron, carbonate. Once again, double replacement. Silver is not dancing with iodide anymore, now it's dancing with carbonate, and iron is not dancing with carbonate, now it's dancing with iodide, so double replacement. How about number 3? C2H4O2 plus oxygen goes to form CO2 and H2O. What is that? Is that a double replacement? Is that a single replacement? What is that? It is a specific category of reaction pertaining to organic molecules that is called combustion. Right? That is a combustion reaction. What would it be going in the opposite direction? If we were taking water and CO2 and putting them together to form that carbon, that organic molecule, what would it be? It wouldn't be a combustion reaction, it would be a...
Soda.
What?
Soda.
Soda?
How many you want?
So CO2 is carbonate. That's what we're starting with.
I know it, I can't think of the word though.
S? Synthesis?
Yeah.
As opposed to decomposition? This is a decomposition reaction. It's just a decomposition reaction of an organic molecule, which is a special case we call combustion. What's the next one? Or next one's number 4. Zinc, sulfate, and lithium carbonate.
Double replacement.
Double replacement again, right? Vanadium oxide and calcium sulfate goes to form calcium oxide and vanadium sulfate. What's that? Double replacement. So far, looks like pretty much everything's a double replacement. Oh, here's one down there. SA, all the way down to number 9. 8 sulfur to begin with, so how many do we need over here?
8.
Put a 1 right there. That leaves us with how many O2? 16 oxygens, or 8 O2s, right? 8 times 2 is 16, if we're going to keep doing the math the way we have in the past. So that means we need 16 over here, but it's an O2, so how many do we need?
8.
8.
Synthesis.
Synthesis. We're taking A and B and making Iggy. Combining things together, right?
You make ABBA movie.
Alright, so do we feel good about this? Are we feeling confident about this? Maybe. Shall we keep going? Combination, synthesis, yes, combination. I believe the book does call it combination, not synthesis, but combination as opposed to decomposition. That might have been what you were reaching for, combination, since that's the specific term the book uses. All right, let's try this one. Silver bromide, gallium phosphate? I think gallium. So, how many silvers do we have on the left? One. How many do you have on the right? Three. So we need to put a 3 here, right? Which leaves us with how many phosphate molecules? One. How many do we have on the left? One. So we'll put a 1 there. Which leaves us with 1 gallium, which means we have 1, which gives us how many bromines? 3. Are we good? Done. Double replacement looks pretty easy, doesn't it? We have 2 combination, we have 1 combustion. Combustion's the one that's tricky. Single replacements, double replacements, synthesis, those, or combination reactions, those are pretty straightforward to balance. It's these really complex guys right here, where we're not just swapping dance partners, right? Especially since combustion reactions are going to include organic molecules, which means it is almost a guarantee that you are going to have oxygen here and oxygen there. Anytime you have the same atom in multiple things, it's going to get hairy. Because you can't just guess, well, what if we go 2 from there and 4 from there, or 1 from there and 5 from there? Like, you can, and then just figure out where it balances out, but that would take a long time, and that's not worth it. So when you're dealing with combustion reactions, my suggestion is to start with your carbons, then move to your hydrogens, and then figure out how much oxygen you need to finish. Everybody follow? That's the best way to tackle those. All right, let's do number 8 just to finish it off. We've done everything else. Dihydrogen sulfate. Hydrogen sulfate. We're on hydroxide. We're on hydroxide. So let's start with this. We're going to have our H2. How many hydrogens do we have over here? 2. Do we have any hydrogen in here? No. So how many hydrogens there? 2. So let's put a 1. Is that going to work? No. You can already see a problem, right? What's the problem? What's the only place to find hydroxide molecules? Over here. Do you see a hydroxide molecule anywhere in here? I do. You have to write it differently. Do you see it now? So, this is our source for hydroxides. So we have identified a problem child. So what do you do when you identify a problem child? Start there. So, this is hydroxide and hydrogen. That's what H2O is. It is a H plus an OH, right? Smart. Oh. Going back in and filling in space does not work well on Smartboard. H there. Squiggly line?
You have to like reset the board.
Parkinson's.
Anyway, alright, we're almost done. Sure, it'll be fine. So that's an H and an OH. We need 3 of them over here, right? Okay, so that means we could put a 3 right here. No, yep, we might have to reset the board totally.
There should be a button. Or.
Is that gonna do it?
No,
No.
no. There's a button, I think, like in the center. It'll get you to like this gray screen.
And then if you tap.
And then yeah, the one to the far.
Smart, yeah.
Hit that. Yeah, because it's really hot. Use your mouse and just click it.
And you have to tap like all 4
Yep,
times.
so then you start the tapping thing. Nope, tap up there in the
Right
corner.
there with the X's, it'll have you do it in each corner.
Yeah,
In the center.
do it with your hand.
Yeah. Do someone else. Put the pen back in the tray.
Well, that
Oh
might be
yeah,
good.
that'll.
There we go. Tap there. No.
Like maybe hit it hard, because these kids kind of hit it.
Punch. I don't think the press, like, okay, fine. Hard?
No.
No.
Well,
Usually
No,
no.
you press
Class
the
is over.
center of
Oh yeah, press the center target and release.
Yeah.
Press the center of the target.
Take your drawing device.
I tried this already.
Or tap the center of the board. Just tap. No.
No.
you might have already screwed it up. Hit,
Yeah.
hit that little button on the
Yeah,
tray again.
reset it.
Oh, that, yeah.
There you go.
Let's try that.
Yep, there it's fine.
There.
You screwed it up again?
You're broken.
I broke it.
Perfect.
Technology, ladies and gentlemen. Let's try
Make sure you
this.
hit it well.
Put that in there, and then touch. Nope.
Try the mouse.
No, they usually use hands.
Yeah.
Like, I've seen too many kids fix this problem. They
Yeah,
literally
like-
jump up, tap it with their hands.
They can figure it out. All right, we'll just do this talking. Or we'll go back to slightly lower tech. As I'm being videotaped with my inadequate use of the resetting a smartboard.
I enjoyed that.
Did you? Press the button.
D600.
With the pen.
It didn't work. Click on the email icon. I touched it. It's not working. Slide the mouse. Now I'm having flashbacks of scenes from Cloudy with a Chance of Meatballs. Slide the mouse. Anyway, all right. So here we have our hydroxyl, right? Here we have water. So we need 3 waters in order to get those 3 hydroxyls, right? So we can put a 3 there. Is that working so far?
Yes.
Here's the problem. Is that going to work? Because that would put us a 1 there. Do you see a problem? Once again, we have a problem because that would give us 1 boron and here we have 2 borons. So let's double all that up, right? 2 borons, not 3 hydroxyls there, but 6 hydroxyls, right? So that's 2 borons to match that. That's 6 hydroxyls to match that, right? But that means we have how many hydrogens from this?
12.
Well, 12 total, but one of them is in that. So how many spare hydrogens do we have? Just 6, right? Because one of those hydrogens in that H2 is part of that hydroxyl. Okay? So you have 6 spare hydrogens. So what would need to go here?
30.
So this 6 applies to that and also to that. Right? So that means that we have how many sulfates? 3 of them. How many sulfates do we have here? 3. So if we put a 1 right there just to show that we actually did the math Is that balanced now? Yes. So this one was tricky for a couple of reasons. One, there was a problem child in there, right? And two, you also had to realize that H2O can also be written HOH. Good for a good problem, though. I like that.
Can you go outside for a second?
What's that?
Check something real quick. What's the reset button? Try it.
You might have to go through the orient.
Okay.
Try to reconnect.
That would fix the electrostatic discharge problem. Oh.
Oh, goodness gracious.
They don't actually show the reset button, they just show it's back. Oh, no, they do show it.
This is where I go take a class on how to use a smart board.
I keep saying,
I think it's fun watching you.
Well, so far I've been able to manage it. It's like, yeah, all right. So now technology is getting the better of us.
Yeah, press the center chart, press the button.
See, it's fun enough.
No? Maybe you should press it when it's flashing, if you first see it and it's flashing. I'm sorry, but you guys have not tried it.
I thought you had to hit it with a pen, but.
I thought you had to hit it with your hand.
See, I'm glad that we had our observation on Tuesday because one of the things that I'm graded on is my ability to use technology, and so far I'm utterly failing. Like, I consider myself good with technology, but the smart board broke, and now I can't fix it. I can click here.
Do the touch recognition.
Now touch it quick, touch it
Really
quick.
touch it?
Nope, it's too late. Try it again.
Oh,
All right, ready, set, go!
Nope.
No, still nothing.
No.
Go back to the menu. And click touch recognition center.
Ah.
That's this.
Okay.
You put your double loop pen. You just work it.
It might just need to be reset.
See, this is the orient button,
Right.
but that just brings us straight to it.
Mhm. Look at
And it
this.
doesn't matter if I click it or he click it, it doesn't matter.
Okay, try it one more time.
Hold it down.
Hold it.
Hold it down.
So-
Do you want to try?
Yeah, yeah.
We're spending chemistry time figuring out our smart board.
Yeah, I have a question about molds.
Go for it.
Okay.
While somebody else plays with the screen, I can answer chemistry questions.
Okay, because, like, I just printed this random thing off. What is the mass of one molecule of oxygen 2? Says mass of 2 moles of H2O.
What's the mass of one molecule of oxygen?
Yeah.
Well, that's one atom, right? One molecule of oxygen is 2 oxygen atoms, because it's O2, right?
Right.
So, you know the weight or the mass of a mole of oxygen atoms, right? Where would you find that?
I got those number 6.
Well, that's the number of atoms it takes to make a mole. What's the weight of a mole of oxygen?
16.
That's for O1, but this is O2. So we've got, but still it's O2, it's a mole. So that's the thing is, if this is a mole, what's the weight of one oxygen atom, right? Yes, okay, so that works. Because it does, if we're talking about atoms, so that's 6.02 times 10 to the 23rd atoms, right? So it's 16 grams, 1 mole of oxygen, even if they're combined together, 1 mole of oxygen atoms is 16 grams. So that's the weight of 6.02 times 10 to the 23rd. How much would 2 weigh?
32.
How much would 2 oxygen atoms weigh? 2 moles, yes, would weigh 32.
Right.
But that's not the question that you asked. You asked, how much would 2 atoms weigh? So 6.02 times 10 to the 23rd atoms weighs 16 grams.
That's true, we could always.
How much would 2 atoms
I
weigh?
did. When I'm unplugging the USB, there's no power to it.
I don't know,
You losing it? So, if you know the weight of
Self-testing.
6 times 10 to the 23rd,
yeah.
alright, so what you do is you just take the weight of that, divide that weight by 6.02 times 10 to the 23rd, then that tells you the weight of 1 oxygen atom.
Oh, so you divide that by that.
So 16 divided by 6.02 times 10 to the 23rd.
Right.
And then since it's asking for 1 molecule of O2,
Mhm.
you just double that.
It's unplugged. That's what it keeps saying, is it's unplugged.
Anyone else have chemistry questions?
Are you sure it's plugged in?
Otherwise, because it was working
This
before.
is, this is a power indicator.
Just making sure.
When you disconnect the communication
Divide by
cable, it also kills the power.
Times 2.
Times two.
So,
Because if you take the
once I
weight of
plug
a
it back
mole
in, you watch,
Okay.
we'll do a quick
and
solve.
divide it by the number of atoms in a mole, that gives you the weight per atom, right? Which should be some really, really small number.
So it'd be like 1.204, 10 to the 24.
Negative 24th.
Oh, I got it. I got it. I think.
It went green!
Yeah.
Now, yep, there you go.
How'd you do it?
I might have done it actually.
Nope, nope, because see, I was clicking there too.
Okay.
You're gonna have to go back and do it again.
I actually,
You're getting
Does
somewhere.
it need the red pen? Is that the deal? It needs the red pen? Nope.
Wait, why is it negative instead of positive?
Why is the negative coming up?
Yeah.
Because it's
That's-
negative, because it's a really small number.
No, no.
Scientific notation times
Yeah.
10 to the negative 23.
Let me get it.
That means it's 0.0000000000000.
On here it doesn't say
Right.
negative, it says 23.
Should be double tap, yeah,
Even,
that one did.
why is it negative?
That's so weird.
Why is it negative?
So,
I'm gonna start over using that.
I'm like
Let's
so
start over
confused
using
because I
that.
keep thinking it's a positive number, so I'm like.
It is a positive number,
Yeah,
but the scientific notation is negative because it's a very small positive
Next one
number.
should come up.
I'm so lost, I'm sorry.
Well, I might be answering a different question than what's on your paper, though. I'm answering the question that I believe you asked.
Okay.
So what was the question on your paper? Let me make sure I'm understanding it
I
correctly.
think when it's green is.
It's like, it's there, it's just getting there, I'm sorry.
No, it's quite all right. They're having fun up on the screen.
Okay,
Alright, try
I just
double.
get confused with how to get there.
What is the mass of 1 mole of oxygen? What is the mass of 1 molecule of oxygen? Yeah, so
Is it like?
the mass of 1 mole of oxygen is 1 mole of O2
Mm-hmm.
is 32, right? Because it's 16 times 2.
Yeah.
But then what's the mass of 1 molecule of oxygen? That's that
Yeah,
divided by
okay.
the number of molecules in a mole, which is 6.02 times 10 to the 23rd.
That's right.
Which is why you get a number times 10 to the negative 20 something,
Yeah,
right? Because it's a really small number.
okay.
That's what the negative in your scientific notation, that means it's a really big number,
Right.
right?
I
Because
just
that
want
means
the
literally
touch,
it's
so let's
6.02
try to
times
use your finger.
10 to the 23rd power.
Yeah.
If it was when it's negative, it means 6.02 divided by 10 to that many power. That's what the negative exponent in scientific notation
Maybe
is.
it's a
So
try again.
you could say that it's like, so 32 divided by 6.02 is going to be 4 point something?
To the negative? Or no, just
Just-
1
just-
or 2 in general?
Right, just 6.02 in general.
It is, what? 32 divided by 6.02.
Correct.
Well, I got like a 5.31.
Yeah,
Okay. Because you
5.31.
said 4. That's why I
Well, yeah, 24 would be 4, so yeah, 5, yeah. So 5-ish, right?
Okay.
But that's, that would be if we're just divided by 6.02,
Right,
not 6.0 times 10 to the 23rd.
right.
So it needs to be 5.02 times lots of zeros before 0.000000502, right? That's what the negative is. So if you actually do 32 divided by 6.02 times 10 to the 23rd, you're going to get 5.02 times 10 to the negative 24th or something like that.
Yeah, okay.
Because it's really small.
Yes.
So the negative in the exponent does not make it a negative number. It just makes it a small. Got it?
Yeah, that makes sense.
You can review that in chapter 1 if you'd like. Scientific notation. Just don't break it, kids.
You broke it first.
All I was doing was drawing on it.
We got the first one to work. It's just the last one.
It's time to go home.
Getting close. Yeah. I mean, we can do some. Well, actually, let me ask you this question. Out of everyone that's left, the thing I really wanted to cover was there you go, the balancing of equations from chapter 7. But then we also have all of the math for the gas law equations from chapter 8. Do y'all feel comfortable with that one? 'Cause that's just, we're in step 2 now.
I got like 8
Just
more.
gotta hit it like 8 times,
We go like 20.
and then go back, press the orient or right click button.
That would go back.
Yeah, that would go back. We want to go forward. Yeah. So, how many other times have you guys run into this in the Smartboard class?
A lot. No, this happens all the time.
It does,
Well, this is the first night that we've used the Smartboard, and the lesson that I'm getting is don't use the Smartboard.
I keep saying they need to have a class, you know, when they hire and do new hire orientation and teach, and it's like,
Well,
and teach this thing and D2L.
right. Well, yes, but D2L has some like online stuff that I can look at. And Smartboards are fairly intuitive, but it's crap like this because here's the thing: we're doing it right. It's not accepting it. So this is not, at this point, I don't think this is human error.
This person's using their finger.
Right, a finger. Because it should just be touch, 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 touch.
Touch me good.
Yeah. And
And then
that,
wait, because apparently this one takes a long time.
so we just have to wait for the next one to show up.
We're touching right, we're just not releasing right.
I hate letting everybody go an hour early. We got stuff we can talk about. Chapter 9.
Quit talking, lady, and do it.
Yeah.
Hey, there's beeps.
Do you got sound on
I've never heard
this
of
thing?
It should be on. I didn't turn it off.
Maybe this cord's a little messed up.
Yeah, volume's on.
Oh,
What?
It might not be wired right.
brain
Well,
table.
but it was working before we started. Like, we got through all of those things, and then it finally started screwing up when I was drawn over here. And then just stopped responding at all.
Yeah, when it stops responding, it's the electrostatic. Okay. Press firmly, finger or pen. Each cross ordered into the white pen, which is Let's start it.
An hour now?
There's
There's
one.
one.
Maybe
Nope.
I feel like if you put too much pressure on it, you're gonna Get that.
Well, it
Chapter
turns
9
green, it means
is
you can
also
look at.
fairly short. Let's look and see if it advances.
Tap it again.
Aren't we taking over?
I think when it turns
more
green is when you're
chapters?
supposed to tap it.
Sort of. We're doing
Oh.
about 4
Wait,
chapters
yeah,
per
wait
week
till
per
it's
test.
done.
Yeah. There's one that's going to be maybe 5, and then another one's going to be maybe 3. Because some of the later ones, when we get into organic chemistry, those are big chapters that we're probably going to have to go slow, and so we may only get 3 on that one. So, but we get what we get. But the syllabus, as I recall when I built it, it was a minimum of 1 per day, and I didn't split one until later on. So I don't think we'd be behind if we just stopped now, especially since half the class isn't here. But,
Okay, where'd they go?
well, some skip.
Oh, wait. Smart
Oh.
one has detected an inaccurate position.
You must re-enter 1 or more.
Operation points. Or orientation points.
Yeah, no, I think I have to. Whoa, no, it didn't. There you go. Oh,
There we go.
no, we're into 3.
Was it green when you? Yeah, it was green.
Wait, why did you pick up that pen?
It was already. I already.
Yeah, she had it.
Okay.
Try to just tap this a few times. Yeah, nope.
So close.
All right, that's enough of that. All right, so I'm gonna take a vote out of who's left. Do we want to work on some problems from chapter 8 tonight? Or do we feel confident in an equation with 6 variables that you could solve for one of them?
I'd rather work for problems in chapter 8.
You'd rather work problems with chapter 8? Okay. We can do that. All right, that's enough. Enough messing with the smart board.
Is that all we're gonna be doing for the rest of the day?
Messing with something?
Yeah, that's what I'm trying to avoid doing, actually. Is nothing other than messing with the smart board.
actually talking about the math.
Right, well, we can do math with whiteboards. But yes, if that's what we want to do, then we can work a few problems from chapter 8. And then call it quits after that. Because if we get 20 or 30 minutes of that, we're not going to start chapter 9 with 20 minutes left. So if you are confident, you could partake of the same course of action that half the rest of the class has. You can skip out, it's up to you. I can tell you that considering that chapter 8 was all about the gas law, conceptually or otherwise, all of chapter 8 homework is going to be about the gas law. So, but yeah, if you're confident in doing the math, then yeah.
That's one good bit. It's everything else.
Okay. Because it really is the trick of, here, let's do this. We're going to go into chapter 8 practice problems.
Oh, and you guys are practicing off of that stuff?
Well, it's that or I pull stuff out of the homework questions. So, well, and which I could do, because I can pull stuff out of the previously done homework ones. Something else that y'all should realize, there are practice problems in between sections in the book as well. So for example, if you want more practice balancing equations, there's about 16 equations that you could practice balancing in the section of chapter 7 on that, and half of them have the answers at the back of the chapter. So, you want to double check your work, you can go there. That's enough, Christian. We're done.
Weird.
And we're done
Probably just make it like these.
with that.
Oh, I did a hard reset. I wanted to check something real quick on the.
You think it's a light sensor thing? It's too
No,
hard for it to
no.
tell?
No, that's actually good.
Gonna edit out the last 30 minutes of dorking around with the screen?
No, that's educational too. No, I was trying to see, I think the glare, you said the glare, looking at the slides, was the reason for not having the lights on?
That, yes, it is harder to see the slides, in my opinion, with the lights on.
Do you guys agree?
Yeah, there's like a little there, right next to the barometer.
Alright.
I mean, we need the lights on for the math that we're about to do anyway, so we'll leave it on. So we'll play with it for a little bit and see. So here we go. So let's try this. A water barometer is 13.6 taller than the HD barometer. This is a conceptual question. So that's not math, but can you answer it?
Okay.
So if we have, if air is, if it is pushing, so what's happening here is the water barometer is 13.6 times taller, which means that the pressure of air is pushing on it and it's getting even taller. So we have, it shows less dense than mercury, it's heavier than mercury, or air is more dense than water. That part wouldn't matter, right? Plus it's wrong, air is not more dense than water. So H2O, the density difference between water and mercury, if it is less dense than that same pressure, would push it more.
What slide is this?
This is from the practice problems slide set,
Okay.
which you could also download and or print out if you wish.
Thank you, Vanna Adam.
You are welcome. Should I like?
Because I'm trying to figure out where it is.
That if you didn't drive, it's online in the content right next to the notes. You probably just didn't download it and print it out because up until now we haven't ever opened one. Did you get it? Okay, you got it. All right. Yeah. So for 2, the answer is that water is less dense than mercury. That's a conceptual question. All right. So a sample oxygen has a volume of 12 liters at 600 millimeters mercury. What is the new pressure when the volume changes to 36 liters? At constant T and N. So, what do we have? We have a volume of 12. So let's do it here. B1 is right there. Here's P1.
Okay.
Yes?
200.
Okay. What's the new pressure when the volume changes to 36? So, we have V2. We want to solve for P2, right? So, PV over T. Temperature is not changing, so the over T part goes away, right?
Mm-hmm.
So PV over T is the equation, right? But T is not, doesn't matter, so we just need the PV. So P1 V1 is equal to P2 V2. We have V1 and P1. We have V2. So let's divide by V2 so that it cancels out, right? So we have P1, V1 over V2 is equal to P2. So does someone have a calculator where we could do that math? Did that right? So we have pressure is 600 times 12, actually we could do that in our heads, can't we?
Can't you just
12 over 36?
12 into 36?
Yeah,
three
which is,
times.
yeah, just 1/3, right?
Oh, yeah.
600 millimeters of mercury
Yeah.
is P1. The initial volume was 12 liters. The final volume was 36 liters, so 12 over 36.
Okay.
3 times.
So 12 over 36 is the same as 1/3, right? So 600 times 1/3 is
Okay.
200. See if we're right. So did we do it right? We have initial pressure, we have initial volume, we have final volume, we need P2, that's what we solved for, right? P2? Yep. So we're going to use Boyle's law, which is P1 V1 equals P2 V2. That's what we did. There's the algebra that we did. So the answer is 200. We did it right. Conceptual check. we have a cylinder containing helium gas, indicate whether cylinder A or B represents the new volume for the following changes. So, if this is helium, if the pressure decreases, are we talking about A or B?
B.
So we're talking about P and V here, right? So as the pressure decreases,
Volume decreases.
pressure decreases, volume should decrease. Right? As pressure decreases, volume decreases?
You talking about the pressure exerted by the plunger or the pressure?
No, the pressure is exerted by the gas.
Oh,
The plunger is free floating. So what is the relationship between pressure and volume? That is the question. Go back and look at, look at that, the relationship between pressure and volume. That's PV, right?
the pressure per case is PA. One is A, two is B. Sorry, I thought you were talking about the plunger.
No. So if the pressure, if we decrease this, yeah, that should be inverse. Let's do this mathematically.
Yeah, it's inverse.
P1, let's just make it equal to 1. V1, make it equal to 1.
This is hard for me to take a test. Good to see him having to work through it.
Yeah.
Yeah.
So we have A or B, new volume for the following. Pressure decreases. So pressure decreases to 0.1. What's 1 times 1? Right? So to get, if this is P2 is 0.1, so V2 would have to be what to also equal 1?
Yeah, it's inverse.
You
Yeah.
lost me on one.
Okay, so I just pick numbers. If the pressure is 1 and the volume is 1, because we're not told what any of these things are, right? This is just purely conceptual. Pressure is 1, volume is 1. So those are our initial values. But the first question is, what happens when the pressure decreases?
Then volume increases.
So I just changed the pressure from 1 to 0.1. So the pressure went down.
So the volume went up.
But if the pressure goes down, they have to be equal to each other. P1 V1 has to equal P2 V2, right? So if this is 1 and 1, from that, and then the new one is 0.1, so it decreased from 1 to 0.1, but in order to be equal, the other one has to go up. So,
Volume increases and pressure decreases. And then if pressure increases, volume has to decrease.
that's the relationship. And we can double check that.
So P would be for number 1 and A would be for.
So it would seem. As volume decreases, gas molecules become more crowded and cause the pressure to increase. And vice versa. Okay, so here's why. It is the plunger. So when we're talking about, so here we have pressure and volume, right? But if the only way to decrease the pressure with the same amount of gas is to raise the plunger so that the same amount of gas takes up more space. So yes, we're changing the plunger. So the only way to decrease the pressure is to allow the gas to occupy more space. So as pressure decreases, the volume increases. And that's because of the impact of the piston. So the same thing as pressure increases, the only way to make pressure increase is to make the volume smaller so the piston goes down. And that's assuming that we have the same temperature and amount of gas, that we're not adding gas to this mixture, right? Here's math. A sample of helium gas has a volume of 120 mils and a pressure of 850 millimeters of mercury. What's the new volume if the pressure is changed to 425 millimeters of mercury? So we're still looking at volume and pressure, right? So PV, P1 V1 is equal to P2 V2. What do we need to solve for?
P2.
The new volume. So we want to solve for this. So, how do we get that? Solve for V2, that means we just divide by P2, right? So that means P1 over P2 times the initial volume is equal to our new volume. So our P1 is 850. Our P2 is 425, which thankfully, practice problems make math really easy. What is that? 850 divided by 425? 2. So our initial volume is 120 mils. What's our new volume going to be? 240. Make sense? Identify what you have. Identify what you need. Plug it into an equation that solves for what you need. Here's that same thing. P1, P2, V1. We need V2. Use Boyle's law once again. $120 times 850 over 425, 240. A sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.7 atmospheres. So, I'm going to put 6.4 liters and 0.70 atmospheres right here over that red balloon. So that we know that that's what we're starting with, right? At 1.4 atmospheres, are we talking about A, B, or C? So what are we changing? When we go from 0.7 to 1.4 atmospheres, we are increasing the pressure. So what are we going to do to the volume? It's still PV. Pressure, volume. So if one of them goes down, in order to maintain that constant, the other one has to go up. So if we are going up with pressure, what does volume have to do? Go down. So which balloon is it? A. The next slide tells us that we are correct. Balloon A. Here's something that we didn't, I mentioned it before. This is just algebra, so I'm going to use this slide here for a second. So our natural gas law is equal to a constant. And that constant is called R. Now you can look up R in any chemistry book other than yours.
Why is that?
Because this is an introductory chemistry textbook for non-chemistry majors. So the degree of detail that this textbook is going into, it does not reach what R is. You can also look it up on Wiki. But another way to write this, you can move this NT to the other side, and you can have PV is equal to nRT. That's just moving this NT over here next to the R, right? This is the ideal gas law. What this means is if you know R, you could solve, and you know the temperature and volume, then you know the pressure and the amount. You have to know everything, just like anything else. But R is a constant. That's what it means here. And so that's how we get the PV. If we put a 1 next to all of these, that's how we get P2V2 over N2T2. Because it doesn't matter what the gas is, there is a relationship between that gas's pressure, temperature, volume, and molar amount that will always be the same. If we change one of these things, it could change any of the other ones as well, unless we put it in a system where the only thing that can change is one variable. So if we keep the amount constant and the temperature constant and change the pressure, it's going to change the volume, right? Change the volume, it's going to change the pressure. You don't have to understand the value of R to understand what it means. There is a relationship between the pressure, volume, temperature, and amount of any gas, and it will always be equal to the exact same thing, that constant. That is why we can do this 1 to 2, initial finding. Because it doesn't matter what the gas is, there is a universal relationship between the amount of gas you have, the pressure that gas has, the temperature the gas has, and the volume that it occupies. Period. Do you guys know how, before you leave, let me ask you a question. You may or may not care. Do you know how air conditioners work?
They suck air in through a filter or whatever and then cool the air as it comes. Like
There are filters.
coils or whatever.
Yes, there are 2 coils. And yes, there is a filter, but the filter is to try and purify the air inside your house. So an air conditioner works to take the air inside your house and cool it down. But the way it works, and the reason why I'm bringing it up, is because it has everything to do with what we're talking about here. So, let's take a chemical, like Freon, which is what you have in your AC, all right? Now, if we were going to take
R14 now.
what's that?
It's actually R14 now.
Oh, true. Well, sure. Because Freon is bad. But here's the idea. If you have something in your house where you have a very, very cold chemical, all right? You run that chemical through a series of things where the temperature of the thing running through it is, let's say, negative 20 degrees C. It's not frozen at that temperature. I'm making this temperature up. It's just cold, all right? If the air that's passing across it starts at, say, 80 degrees, well, this is temperature. It starts at, say, 37 degrees Celsius, which is pretty toasty in your house, right? 98 degrees. Yeah, that's pretty warm. So what's going to happen is the heat from the air as it passes across it is going to be absorbed into this liquid as it goes through this coil, right? So the liquid that comes out of this coil will be warmer than negative 20. Let's say it will be rise all the way up to 10 degrees Celsius. Well, as this liquid warms, it cools the air. So the air that's coming off on the other side of this is coming off at a nice 27 degrees Celsius. A nice cool temperature. The air gets cooler, the fluid warms up. Perfect! We have now cooled our house once. Problem is that this liquid right here will no longer be good for cooling our house. Because it's not nearly as cold anymore, right? So how could we make that cold again?
Use a compressor to decrease the volume, and then an air exchanger on the other side to let off that waste heat.
PV over T. If we can take something by changing the pressure and the volume, by increasing or decreasing the pressure and the volume, which is what a compressor in your air conditioner does, that's the really expensive part of your air conditioner is the compressor. What it does is it takes this thing right here and it compresses it so that the pressure goes way up the volume goes way down, and what that does is it really changes the temperature. It makes it go way up. So now outside, in that thing that you have outside your house with the big fan blades, right? What it's doing is you have another set of coils that is passing through. Except now the stuff passing through that coil is up at 60 degrees Celsius. And the air outside, 37 degrees, right? So as the air passes through this, it starts at 37 degrees. And what's going to happen to it? This stuff, the warm stuff here, is going to heat up the air. So the air is going to come out and be a little bit warmer, 45 degrees, see?
So it's gonna go from about 98 to,
I'm making up numbers,
okay.
but it'll cool it. So the idea is we change the pressure and the volume, which spikes the temperature. The reason why we need to spike the temperature is we need these coils to be hotter than a 100-degree day outside. So that when we pass that 100-degree air over those coils, if those coils are 140 degrees, then those coils are going to cool off and warm up the air, right?
Mm-hmm.
Even though it's 100-degree air, it's still going to become 110-degree air, right? And that's going to cool down the liquid in that coil. Now, what do we do next? We pass that back into the house, except right before it gets to those coils, there's a place where it can expand. So now all of a sudden the pressure is going to go way down, the volume is going to go way up, so what's that do to the temperature?
What is it?
Makes the temperature go way down. So now we're back down to negative 20 degrees C. You can pass your air over the coil again, warm up the coil, comes back through a compressor to make it really hot so that we can transfer some of that heat to the air outside. Then it comes back in, expands so it cools down really fast, and that's used to cool the air, and then this cycle just keeps getting repeated over and over and over again. The whole idea is outside you want that liquid to be hotter than the hot air outside. That way some of the heat that it absorbed in here is transferred to the air outside. That's why even on a 110-degree day, 105-degree day, whatever day it is, you go out and stick your hand over that fan, and it will be hot.
Mm-hmm.
But then when that cools off and is allowed to expand again, it gets cold. That is how an AC works. That's how the AC in your car works. That's how the AC in your house works. And it has everything to do with the natural gas law that we just talked about today. Well, that's what the light crashed. Everything to do with this. Initial temperature volume during our compression. So we have one change right here where we increase the temperature so that we can get rid of the heat. And one change in here where we decrease the temperature. And that's neat. It makes sense, right? But it's like, well, how does it do that? How does it increase the temperature and decrease? We use electricity here to pressurize that fluid so that the temperature goes up. We increase the pressure, we decrease the volume, the temperature spikes. Why? Because if you decrease the pressure, or increase the pressure and decrease the volume up here, the temperature is the only thing that can change. Because it's a closed system. We're not adding more Freon, right? We're not losing it. Well, you shouldn't be losing it. So the only thing that can change is the temperature. And if you can spike the temperature high enough that it's hotter than the hot air outside, it'll still lose heat to that hot air. The exact same thing cools your refrigerator. So why is it that if your house is ever hot, you ever been like kind of hot when you come outside, you can stand in front of your own thing, or you can just open up your refrigerator door? Or if you have your freezer, just open up the freezer door and like shove your head in there for a second. Here's the thing. That's not going to cool your house though. Why not?
Because it's a closed system, you just opened it.
The heat that it's taking out of the air in your fridge, where's it dumping that heat?
Into the back, out the back.
Out the back of the fridge into your kitchen.
Mhm.
So when you open the door, you're just letting the heat back into your fridge. And so you just spent a lot of electricity moving heat for no reason. It's not going to cool your house.
Unless you want to cut a hole in the house, size of the fridge, and put the back
And
end
then
sticking
seal
out.
it. Exactly, that would do it.
And it
That's
becomes
why
a window unit.
Right. That's why yes, that is the idea behind a window unit. Well, that's why ACs are expensive, but that's why there's the outside thing. You have a point where it expands down here at the part where you're cooling your house, and then that air never leaves your house. It gets sucked in from your house, passed over the thing to cool it, and then back out to your house. The stuff that's outside sucks in outside air and passes it over the coils and leaves it outside. It absorbs heat from your house and then warms up the outside air. And then what can you do to completely defeat the purpose? Open your door and let the outside air in or the inside air out, which is exactly the same thing as opening your fridge. Like, it's just an exchange of heat, but it has everything to do with the way this gas law works. It's just math. And a spiffy chemical that can go through really big temperature changes over a short period of time. Here, you want proof? Go get a can of compressed air. They're cheap at Walmart. It's compressed air, specific volume, specific temperature, specific pressure. But you let some of that air out. What's going to happen to the can?
Freeze your hand.
It gets cold really fast. Why? Because as the air is leaving that can, what's happening to it? It's expanding. The pressure is dropping. The volume is spiking. So what's going to happen? What has to change? Something has to pay for that. Temperature. The temperature drops. The can gets cold because the energy that was part of the temperature of the can is the energy that is being used to pay for that increase in volume. It's not free. That's the concept behind your AC. And that is this equation. Just with a lot of tubing and chemicals that are bad for the environment. And electricity. So anyway, you can feel free to dead if you wanted to. I just wanted to point out, because that's one of those how does it work that a lot of people don't have any clue. So it works, here's how it works. I press the on button, and then it gets cold. I change my thermostat, and it gets cold. Yes, but why? Because of chemistry.
I can understand that, and I still conceptually struggle with I know the theory.
All right, do we need to do more math, or are we good? These problems are in there. We worked through some of them. You can download them, look at them. There are problems in the book, in the sections for each law. Boyle's law, Charles' law, right? And there's also problems at the back. My suggestion, maybe work through some of the ones where the answer is provided. Those are the ones in red. Because the homework problems are going to come from the one in black. You can work through those too, and then
Some of the same.
make your homework faster, or you can wait until you figure out which ones I'm going to use.
Hydrometer.
All right?
I work on all the cars, so a lot.
I'm here as long as you guys want to hang out. But if you guys are, so if you have specific concerns, we can keep going. As long as I didn't just leave black marks all over my head. Yeah, it's like chalk. Here, let me rub my face. All right. So there will be a new homework opening up tomorrow morning. It will be due before class begins next Thursday. Probably. And what else happens next Thursday?
Test.
Test number 2. 8-week course, every other week. Get a test every other week.
Oh, every other.
Every other week. Homework every week. Test every other week. But remember, it is only as cumulative as the concepts require. We're getting deeper into the actual chemistry, guys. Isn't it exciting?
So maybe we don't have to do that much math anymore?
No.
All math.
There will still be math. We're just getting deeper into the. Once we get into the organic chemistry, then I'm going to say there's going to be less math in the organic chemistry sections because that's more conceptual and just reactions and shape of molecules. But there could still be math in there as well for free energy change between exchange or how much energy you get out of that combustion reaction. That kind of thing. So there's always room for math. That's a beautiful thing about chemistry. It's really amenable to asking questions in terms of numbers. Or concepts, too. But
Too much math.
This is a little frustrating because this is basically Chem 108, except that they crammed all this into like the last 4 weeks.
well, this is supposed to be, I think, an alternative to 108 for nursing
I used to take
students.
that one first and then take.
Yeah, if you
And
didn't
then
have
this-
chemistry in high school, you would do
Oh,
108.
First,
Yeah.
right.
Which was physical science, but
Maybe once you skip over that,
me?
yeah.
Oh no, no.
Mine signed off and let me skip over it.
All right,
Your
so let's see.
Jeannie?
So Megan
Jeannie,
wasn't
was that
here,
her?
Kenya was not here. We had everybody else here, right? Except for
We didn't have the one girl that.
yeah,
said
I knew she was going to be gone, and then Megan was not here either because she's only been here once. Everybody else
She's
has
only been here once.
Once. Okay.
And she hasn't dropped?
Nope.
Can't drop now.
She did. She can't drop now, and she did really well in the first test.
Huh.
See, here's the thing.
Maybe she really took you literal when you said, well, you don't have to be here.
Well, yeah, except that I also said, except Columbia College requires you to be here,
Yeah.
right? Like, so
You might want to send her an email and go, look,